Hello everyone, this is Joshua Foreman. I'm here to present my Lab 6 magnetic molasses. So, the purpose of this lab right now is to demonstrate Faraday's law in action with the bar magnet falling through conducting metal tube and to model this phenomenon computationally. For our analysis, we measure the time it takes for the magnet to fall through the tube. We take the average over 5 trials. We create a computational model with glow script using mathematical formulas that are involved using the physical principles, which will be described below, using the formulas that predict the magnet's motion, and we're going to compare the results. The results in question, average time to drop, empirically it was 1.44 seconds, and a computational model recorded 1.54 seconds. So the first physical principles at play, we have Faraday's law, which describes that the EMF generated through the change in magnetic flux is equal to negative direction of d flux dt. And the negative direction specifically is described by Lenz's law, which says that the current flows in the opposite direction to d flux dt. Newton's third law, which says that the force of the magnet on the tube, on the current, is equal to the force from the tube onto the magnet. And the position update formula just says velocity is change in position over change in time. You can algebraically rearrange that to get the actual formula for position update. Newton's second law and velocity update go together, which is that acceleration equals the net force over the mass of the object in question, which is equal to the change in velocity over the change in time. Again, we can actually do the velocity update formula by just rearranging the equation to get final velocity in terms of initial velocity and F net over m. So some assumptions we're making going into this lab is that there's negligible air resistance, that the metal along the tube is evenly distributed, and that the bar and the tube were perfectly vertical when we dropped. Here's a photo of the experiment. Here's my lab partner dropping the magnet. Notice, I guess it's not perfectly vertical. More on that later. So here's the glow script code that was used to generate the results. I gotta say it didn't work all that well. It took me a while to just look through it, and I could not figure out what was wrong with it. So I apologize because the computational model didn't actually show a good picture. Lastly, what if the resistance was close to zero? Well, we know that EMF equals the resistance times the current, and so if you rearrange that algebraically, you get that the current equals the EMF over resistance, and if the resistance is really small, then that means the current's really big, which means that the induced current would become very large and would cause an upward force that dramatically slows down the fall. And if we cut holes in the tube, well, the induced currents would be less, and they wouldn't be loops, which would drastically decrease the upward magnetic force. Sorry, I'm running low on time, but one thing I wanted to say was that the times were very different. Like the average was about like 1.404. But the actual times among each trial differed by like half a second sometimes, and I believe it has to do with the bar not being vertical during some trials. Not the bar, like the tube. So that could also cause a discrepancy between the computational model and the physical model. Have a wonderful day, and good luck on the final.